Hi, this is Sophia Zane from Mr. Farrar's Period 3 class, and today I'll be teaching the concept of curve sketch. Curve sketch is a very simple, albeit lengthy and time-consuming process, so let's get straight into the video. So say we have a function y is equal to f of x, and we want to be able to graph this thing without actually having to use the little chart, which can be time-consuming. So, in order to do that, we have to find several important things regarding this graph, which include the domain, any x or y intercepts, any horizontal or vertical asymptotes, the symmetry or the period of the function, and the first derivative of f of x, which will allow us to find when it's increasing or decreasing, which will then in return allow us to find any local maxes or mins. And then the second derivative of x, which allows us to find when it's concave up or concave down, and any points of inflection on the graph. And some people will be asking me, well, why do we need to find symmetry and period if we have all this other stuff we need to cover? And it's just a personal opinion, but I honestly feel that symmetry and period give you an idea of whether or not you're drawing the graph correctly. But I can understand and see some people thinking that it's redundant or kind of pointless to a certain extent. So if you don't want to, you don't have to do this, but just keep in mind that throughout this entire video, I will be finding the symmetry and period of all the functions. Alright, let's move on to our first example problem, which is y equals sine of x minus cosine of x. And as you guys can see here, I already pretty much worked out the entire problem. And this is because these problems are once again lengthy, so if I were to sit here and actually do the problem step by step, this video would probably end up being like half an hour long. And also, most of the stuff I'm doing here is already stuff you know how to do, such as finding the derivatives and testing values or finding intercepts. This is all stuff you already know how to do, so I don't really find a huge need to recover how to do this. So I'll just mostly be outlining the general process of doing this. Okay, so we have our function, which is y is equal to sine of x minus cosine of x. The domain of this function is all real numbers. Intercepts are found to be 0, -1, pi over 4, 0, and 5 pi over 4, 0. There are no asymptotes for this function, and the period is 2 pi. If you remember from trig, sine and cosine both have periods of 2 pi. And now we can find the first derivative of this function. And we set that to equal to 0 because we want to be able to find critical numbers so we can make the chart to test when f of x is increasing or decreasing. So we end up getting that x is equal to 3 pi over 4 and 7 pi over 4. And then we make the chart. I guess it makes more sense to write it out this way. Okay. So we make our chart, and then we have to test these intervals to see when f derivative of x is positive, which means that f of x is increasing, or when it's f derivative of x is negative, which means f of x is decreasing. So we test all these intervals, and we get that along 0, 3 pi over 4, f derivative of x is positive, which means f of x is going up or increasing. And then 3 pi over 4 to 7 pi over 4 is negative, so that means it's along f of x, along this interval f of x is decreasing. And then 7 pi over 4 to 2 pi over 4 is the first derivative is positive, so that means that it's increasing. And when it's going from increasing to decreasing, we have a local maximum. When it's going from decreasing to increasing, we have a local minimum. So at 3 pi over 4, it's going from increasing to decreasing. So we have a maximum. And plugging this into the original equation up here, we get that it's equal to root 2. And then the local minimum is 7 pi over 4. And because it's going from decreasing to increasing. So that means that the local minimum, by plugging it back in, is -2, 7, and at 7 pi over 4. Then we find the derivative of the first derivative, which we get the second derivative, and once again we set that equal to 0 because we want to find critical values once again so we can make another chart for concave up and concave down. And solving it, we get x is equal to pi over 4 and 5 pi over 4. These, once again, are the boundaries to our chart, and let me rewrite it this way. And then testing values once again to find when it is concave up or concave down. So along 0 pi over 4, second derivative of x is positive, which means f derivative of x is concave up. And then along pi over 4 to 5 pi over 4, the second derivative of x is negative, which means that f of x is concave down. And then 5 pi over 4 to 2 pi is once again positive, so that means it's concave up. And then points of inflection are pi over 4 to 0 and 5 pi over 4 0. And it's mostly coincidental, but these are the same values of our x-intercepts here. So yeah. And then we plot these points down as they kind of serve as guidelines for where the graph goes. And then I mostly pay attention to concave up, concave down. So along 0 pi over 4, it is concave up. And then pi over 4, 5 pi over 4 is concave down. So it goes up, and then it goes down. And then pi over 4 to 2 pi is concave up. So yeah, it's just like that. And if the question was asking us to graph 0 to 4 pi, this is when period becomes useful, as we don't have to find more values for 2 pi to 4 pi, as it's simply just a repeat of this graph. So that's one way period becomes useful. Alright, let's move on to the final example, which is y is equal to x over x squared minus 9. This problem is actually not all that much more difficult. It's just a little more time consuming since the derivatives are a bit longer to do. But anyway, so the domain of this function is negative infinity, negative 3 to negative 3, union negative 3 to 3, union 3 to infinity. And there only ends up being one intercept, which is at 0, 0. There ends up being 3 asymptotes total, 2 vertical, 1 horizontal, and these are x equals 3, x equals negative 3, y equals 0, and if we end up plugging negative x, y into this thing, we end up getting that this function here has origin symmetry, which will help us when drawing a new graph out or making logical sense of a graph, so just keep that in mind. So now we can find a derivative of this thing, and it ends up being this thingy, and it's undefined at 3 and negative 3, so that ends up being our critical numbers. And once again, we make the graph or the chart, and this graph is actually really boring and ends up just being negative the entire time, which means that this graph is just going down. Y is just basically going down forever. And this then means that there's no maximums or minimums. And then we can find the second derivative of y, which then looks ugly, but there ends up being some simplification in between. So you end up getting something that's actually not all that ugly. And then the critical numbers are positive, negative 3, and also 0, because that's when it's equal to 0 and it's undefined or unable to be evaluated, basically. So then we make the chart again, and we test the intervals, and we get that on negative infinity to negative 3, it is negative, so concave down. And then negative 3 to 0 ends up being positive, which means it's concave up. 0 to 3 is concave down because it's negative. And then 3 to infinity is positive, so concave up. And then based on this little chart here, it looks like we have 3 points of inflection, but we actually only have one, because if you remember earlier, we have vertical asymptotes at 3 and negative 3, so we only have 1 point of inflection, which is 0, 0. Sorry guys. Okay, so now we can actually draw out the graph. So we have 2 vertical asymptotes at negative 3 and 3, and they only give us 1 point, which is 0, 0, 0, so that's the only point we have. And there's also a horizontal asymptote at y equals 0. Okay, So that's basically the only background information we have given this graph. And now we look at our concave up, concave down. So from negative 3 to negative 3, it is concave down, so something like that. And then negative 3 to 0 is concave up, so something like that. And then 0 to 3 is concave down, so something like that. And then 3 to infinity is concave up, so something like this. And then sometimes I know that you're tired and you'll make silly mistakes where you'll like draw something like, oh, this, but then this goes down here like that. And this is when origin symmetry is really nice because it helps you make sure that your graph makes logical sense in a certain way. So if this was what you accidentally drew the graph like, you can kind of tell that it's not right because it doesn't obey origin symmetry. So in this case, you would know that, oh, I did not draw the graph right. It's supposed to look like this. Alright. So that concludes my video. I hope it was helpful and made sense, and thank you guys for watching.